Last time we talked about solving systems of equations graphically. What we're going to work on now is solving systems of equations algebraically. Um, so we'll jump right in. We saw some examples of systems of equations last time, so I will work out a few more examples now, only doing them algebraically instead of with your graphing calculator. So, from your textbook, I'll jump right in to example 1 off of page 441. In this case, we've got a linear quadratic system of equations given as 5x minus y equals 10 and x squared plus x minus 2y equals 0. And we'll talk about, here goes my focus again, we'll talk about two different methods of solving these algebraically. The first, and one I tend to use a little bit less, is substitution. So in substitution, your goal is to isolate one of your variables, either the x or the y, and then use that to substitute into the other expression. What appears to be easiest to do in this particular case, and this will be our substitution, is if I take my first expression and rearrange it to get y by itself. By adding y to each side and subtracting 10 from each side, I can make the statement that 5x minus 10 equals y. And again, to solve both equations, my y value would have to be equal to 5x minus 10. And that is an expression I can substitute into my second equation and end up with x squared plus x minus 2 times my expression for y. Notice that when I substitute it in, I put it in brackets. That's because in this particular case, the 2 needs to multiply all of y, which in this case is all of 5x minus 10. Typically, when doing a substitution, sticking brackets around what you've substituted in is a good idea, because that will maintain your operations on all the parts that you need them to be maintained on. Now, if I expand the brackets and simplify, I have x squared plus x minus 10x plus 20 equals 0. And if I combine my like terms, I have x squared minus 9x plus 20 equals 0. And that's a quadratic to solve. And we've talked about a number of different ways before to solve quadratics. In this particular case, factoring looks like kind of a nice way to go in this one. If I have two numbers that add up to negative 9 and multiply to 20, in this case that would be x minus 4 and x minus 5. If that product equals 0, then that leads me to statements that x equals 4 or x equals 5. Now, to completely solve this, I don't just find values for x, but I also need to find values for y. I can use these x values in either of the two equations that I have at first. I'm probably going to go with this one, since it's the simplest one I've got. So if y equals 5x minus 10, then when x equals 4, y is going to equal 5 times 4 minus 10, which works out to be 10. And when x equals 5, y is going to equal to 5 times 5 minus 10, or 15. So my two solutions are x equals 4, y equals 10, and x equals 5, y equals 15. And you could put both that x and y value into both equations to verify that if you needed to show that it all works out. I mentioned that we were going to have two different ways to talk about this. Our other is elimination. And in elimination, effectively you are trying to get one of your variables canceled out. And I do want to stress, particularly when you've got quadratics involved, as you do in this case, it wouldn't be enough for me to just cancel these x's out, because then I'd end up with an x squared still left over here, as well as the y's. So it's going to help us a bit more to match up our y's to get rid of them. So in this case, I would take my first expression and multiply it by 2. That would leave me with 10x minus 2y equals 20. Don't forget to multiply the right side as well as the left side by 2. I'm going to leave my first expression alone. X squared plus x minus 2y equals 0. And then I'm going to subtract that second expression from the first one. No x squareds minus an x squared will be negative x squared. 10x minus x is 9x. And negative 2y minus negative 2y is 0. So my y's have canceled each other out. And 20 minus 0 is 20. If I bring everything to one side, I end up with the same quadratic that I had above, which means it would have the same solution, which it should. Now again, had I chose, I could have multiplied the second expression by 5 to make my x's match up, but that would have left me with a 5x squared and values in y in the same expression, which I wouldn't have then been able to solve. So, this is our solving of systems of equations either through substitution or through elimination. I want to do a couple more examples of working with this. One where we get to make up our own word question, or make up our own equation from a word question, which I know everybody loves to do. I feel I should fill this dead space with something, but I don't know what, so I don't. Alright, now I'll probably be a little bit in and out of focus here, so bear with me. Example 2 on page 443. Yep, there we go. Okay. So, this one deals with Glenn. Glenn loves to challenge himself with puzzles. He comes across a website that offers online interactive puzzles, but the puzzle makers present the following problem for entry to their site. So you like puzzles? Well, prove your worthiness by solving this conundrum. Oh, challenge accepted. Determine two integers. Alright, first out. As soon as it says determine two integers, call them something. And I'm just going to say two integers x and y. So what about these two integers, you ask yourself? Determine two integers such the sum of the smaller number and twice the larger number is 46. So let's call this our smaller number, and this our larger. The sum of the smaller number and twice the larger number equals 46. There's my first expression, my first equation. Also, when the square of the smaller number is decreased by 3 times the larger, the result is 93. So, this is what we're asked to find, are two integers that satisfy both these conditions. So, I could do this by either substitution or elimination. I think I am going to go with elimination. I am a little bit partial to it, although either way would work. I'm going to call this equation 1 and this equation 2. So, it would be kind of tough to make my x's match up. I'd have to square things up here, and that would lead to some unpleasant cross terms. So I'm going to match up my y values, which means I'm going to multiply equation 1 by 3 and equation 2 by 2. That gives me 3x plus 6y equals 3 times 46 is 138. The thing that a lot of people tend to forget is to multiply the right-hand side of that as well. I'm going to take equation 2 and multiply it by 2. That would give me 2x squared minus 6y equals 186. And now in this case, I'm going to add my two expressions together. Because no x squared plus 2x squared would give me 2x squared. 3x's plus no x's would give me 3x. And 6y plus negative 6y, they end up canceling out. And I add these together, 138 plus 136, pardon me, 138 plus 186 is 324. So that leaves me with a quadratic in x to solve. 2x squared plus 3x minus 324 equals 0. I might concern myself a little bit that this number is going to be kind of large to work with for factoring, but I know my numbers have to be integers, so that means there do have to be fairly nice factors for this expression. So I'll think about possibilities. I need two numbers that add up to 3 and that multiply to, focus back. Oh, it's going to be that way. Give me a second. I don't know why this works. Or if it works. But it works sometimes. Alright, I need two numbers that add up to 3 and then multiply to negative 648. So I need to think of some factors of 648. Well, there's 2 and 324, but that's probably not going to get me anywhere. I can cheat a little bit since I got the old calculator right here. 3 and 216, also not going to help me out a whole lot. 4 and 162, ooh, it's going to take a little while. 5 is obviously not going to work. 6 and 108 doesn't help me out any. 7 is also not going to work. 648 divided by 8. 8 and 81, getting a little closer, but still a ways out. 648 divided by 12. 12 and 54, also not helpful. 648. 14 doesn't get me there. 648 divided by 16. Not like that. 648 divided by 16. Nope. 648 divided by 18. 18 and 36. Getting a little bit closer. Divided by 24. 24 and 27. Whew, that took a little while. Alright, so those are my two numbers. One, the larger has to be positive, so I end up with 2x squared minus 24x plus 27x minus 324 equals 0. I can bring a 2x out of these. Ooh. I can bring, I must be able to bring 27 out of those. Which leaves me with factors x minus 12 and 2x plus 27. The product of which has to equal 0. So x could equal 12 or negative 13.5, which I get from there. Now, our last problem is that the numbers have to be integers. That means this falls out because it is not an integer. So my value for x has to be 12, which leaves me with a y value. If I go back to expression 1, x plus 2y has to equal 46. So 12 plus 2y has to equal 46. So 2y has to equal 34. So y has to equal 17. So there are my two integers that satisfy both expressions. Lastly, I wanted to show one example of a quadratic-quadratic system. This is example 4 from page 447, where we've got two quadratics to solve. 3x squared minus x minus y minus 2 equals 0. And 6x squared plus 4x minus y equals 4. Already things are pretty straightforward. I may just end up putting my numbers on the right side just for a little bit of order to the whole thing. I subtract the second equation from the first. 3x squared minus 6x squared is negative 3x squared. Negative x minus 4x is negative 5x. Negative y minus y cancels, and 2 minus 4 is negative 2. If I bring everything to one side, I'd end up with 0 equals 3x squared plus 5x minus 2. Two numbers that add up to 5 and multiply to negative 6 would be 6 and negative 1. So I can decompose the 5x into 6x minus x. I can factor a 3x out of the first two terms and a negative out of the next two, which leaves me with factors of x plus 2 and 3x minus 1. So from there, x has to equal negative 2, or 1/3, obtained by setting both factors equal to 0. And if I rearrange my second equation, I get the statement that y equals 6x squared plus 4x minus 4. So at x equals negative 2, I just realized my in-screen is going to move, so I'm going to shift this over a little. Y equals 6 times negative 2 squared plus 4 times negative 2 minus 4. Or, negative 2 squared is 4, 24. 24 minus 8 is 16, minus 4 is 12. And at x equals 1/3, y is going to equal 6 times 1/3 squared plus 4 times 1/3 minus 4, which would work out to, this will be fun, 196 will be 2/3 plus 4/3 minus 4. 2/3 plus 4/3 is 6/3, which is 2. 2 minus 4 is negative 2. So my solutions are x equals negative 2, y equals 12, and x equals 1/3, y equals negative 2. Okay, those are a few examples of solving systems of equations algebraically. There'll be a few sample questions or questions to try in the Google Classroom. All right, that's it, everybody. Thank you.